Professors FM.
Welcome to Why This Universe. You're about to listen to the Ask Us Anything segment that Dan and I host on our Patreon. If you want to submit a question for the next one of these that we do, you can go to patreon.com/whythisuniverse and sign up for as little as $3 a month. And that helps us keep the show going. Thanks for listening. You're listening to Why This Universe, a podcast where we break down the biggest ideas in physics. I'm Shalma Wegsman.
And I'm Dan Hooper. Hey, Shalma, how are you? It's been a minute.
Hey. Okay, cool. So let's get into it. The first question is from Craig.
Okay.
And he says, I'm less than a novice and I have a question on the twin paradox, and says, if you say this is pretty close to being right, you will make my day. So let's see. So if my twin leaves me at the speed of light and comes back in a year, I think that I will see him, but I will not be able to have a reasonable conversation with him for a year. Like any message sent at the speed of light, there's no way to change the information in that message, and while it's possible to send a response, it takes time for the response to be received. So I think there's two things going on. One is the idea that it takes messages, right, some time to send, because any message can only travel as fast as light can go, so it does take time to reach your twin that's out in space. And yeah, I guess if your twin especially is moving at the speed of light, no message will be able to reach them in general. But that is different than the twin paradox.
Yeah, I mean, let's say that your twin is not moving at exactly the speed of light, but I don't know, 99% of the speed of light or something. Then eventually your message, if you're using light, something traveling at the speed of light, it will eventually catch up with them. But it'll take a while, but like you said, Shalma, that's not the crux of the twin paradox. The crux of the twin paradox is that the amount of time that passes in the two frames of reference are different. So when your twin returns, that you'll be a different age than your twin, right? In particular, if you're back on Earth, when they get back after their round trip voyage, they will be a lot younger than you are, depending on exactly how fast they were traveling and for how long.
Right, and that's because when you move closer to the speed of light, your clocks tick slower. So less time passes for the twin that's traveling at the speed of light or near the speed of light than it did for you back on Earth.
Exactly.
Yeah. My understanding is that the paradox comes from the idea that before your twin returns to Earth, you're not sure which of you is the one who's older and which of you is the one who's younger.
Well, so actually, I'm not exactly sure the historical, where the phrase twin paradox came from and what the original people meant when they used that phrase. I've heard different people say different things, and they can't all be right, right? So I've heard some people say the quote unquote paradox is that you and your twin, who are by definition the same age, aren't in this. And okay, that's true. That's fine. Um, I've also heard people say that the paradox is one having to do with just like special relativity and well, you could do the calculation in the rest frame of Earth, in which case the moving twin is the one off in the spaceship, and they're the one that is younger when you get brought together. On the other hand, you could do the same calculation in the rest frame of the spaceship, in which case it's the Earth that's moving, and you should get the opposite answer. But it turns out if you have general relativity, you can parse that, and there's one right answer to which one is the right answer.
Especially if they turn around and return to Earth, right? Then there's some
right, because they experience acceleration.
Right. Yeah, this is only true for things moving at constant velocities.
So I don't know. I'm not exactly sure. I think different people mean different things by what is the quote unquote paradox here. But there's not a unsolved paradox here. This is a very understood problem. Right. This is solved physics.
Yeah, it's more of
at least once you had general relativity in hand.
Yeah, it's kind of just like a thought experiment that we get an answer for from relativity.
Mm-hmm.
Okay, well, thanks for the question. Okay, so the next one's from Rad.
Ah, rad.
Rad's back.
Rad's my favorite. Keep coming, Rad.
We love all of our Patreons equally. But last March, the Ice Cube collaboration published a paper in Nature Physics describing a search for decoherence of atmospheric neutrino oscillations due to quantum fluctuations of spacetime. Are there plans to update the analysis and potentially extend it over a larger energy range? If yes, when might we expect the update?
All right, so yeah, I mean, Rad, you're right that last year this paper came out from the Ice Cube collaboration, and let me kind of unpack it for listeners first. Like, so quantum decoherence is an idea where it's like quantum information kind of gets lost either to the environment or otherwise as a state evolves. So in this case, we're talking about neutrino flavors. So neutrinos come in three flavors: electron neutrinos, muon neutrinos, and tau neutrinos. And in principle, different neutrino flavors can oscillate into other flavors and things like this. But in some theories of quantum gravity, that information can kind of get lost. It can undergo decoherence, and you might just end up with a state that can't remember the origins of its, flavor composition. And yes, the Ice Cube telescope, this big high energy neutrino telescope into South Pole, has done studies of neutrinos, both atmospheric neutrinos and astrophysical neutrinos, looking for signs of this, and they haven't seen any. And Rad's right. They're looking kind of in a specific energy range where they think they're going to have the most power and things like this. And ideally, one day you would do this over a wider range of energies and maybe a bigger set of data and things like this. I'm not off the top of my head sure whether there are active groups working on that right now. I bet I could find out, but eventually that sort of thing will get done. I'm confident in that. I don't know if anybody is doing it as we speak. I worked on this stuff like a long, long time ago. I think when I was in my first postdoc, I thought about ways to use neutrino telescopes to test these sorts of like weird quantum gravity effects. Um, I remember having like referee reports to some of these papers at the time saying this is completely unrealistic and you'll never be able to test these things. It's really like very satisfying to see real data analysis being done,
Mm-hmm.
20 years later,
Yeah.
which is actually testing this stuff.
Yeah, that's cool. Does it make you feel old?
Yeah, 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 no, totally. But I also don't even think at the time that I argued with the referee. I was like, yeah, you're right. This will be really never going to be able to test this. It's super futuristic. But here we are. We're living in the future. So it's pretty
Yeah,
great.
the future happens eventually, I guess.
Yeah. Yeah.
Okay, cool. So Rad asked two more questions that were about the recent DESI result. So
Oh,
showing
yeah.
that
Okay.
maybe the cosmological constant that's responsible for our universe expanding might not be so constant after all.
Hmm.
Okay, so the first question. So the DESI results are out, and the tension with the constant dark energy grew to 4.2 sigma when including the CMB and other measurements. Do you have a favorite theory horse in the race to overtake the cosmological constant if the significance rises above 5 sigma in the next DESI data release?
Yeah. And I'm still trying to figure out what I should think about
Yeah.
this. So, on the one hand, I mean, so I was just at a conference like literally yesterday,
Hmm.
and we talked about this, and we had a big discussion section on like different cosmological anomalies, and like this was one of the ones that definitely got people excited. Probably like it was maybe the second most compelling one behind the Hubble tension.
Hmm.
So pretty lot of interest. But still, most people think it's not going to be new physics. When you ask them. Um, but
And if it's not,
you
it's not that the error isn't there. It's that maybe if we're more precise about some feature of our model, then the discrepancy goes away. Is that the idea?
or there's some systematic error
Yeah.
somewhere in that analysis pipeline. Like this stuff is hard, and most of the time when things look weird, it's because you did something a little wrong. But it could also be new physics. You can't at an early stage. It's very hard to tell those things apart, which is like why you want to measure things in multiple different ways. That would be subject to different systematic uncertainties. Um, this is why we're not sure the Hubble tension is real. Like it very well might be, when you measure the Hubble rate, the rate of Hubble expansion, the rate at which the universe is expanding, using certain kinds of measurements in like kind of the cosmologically local environment, or when you infer that same number from things like the CMB, you get, 5 sigma different answers. And maybe that's new physics. Maybe that's telling us that the conventional cosmological model needs new components to it to make sense. Or maybe it means there's something in that data pipeline that we don't completely understand. And it's really hard to know which yet. And I think we're in a similar situation with DESI. Um, but that being said, I've been educating myself about evolving dark energy models because of this. It's not that I didn't know anything about it, but I'd never really worked on it. And one thing that made me skeptical for a long time about evolving dark energy models is they almost always evolve a very, very, very light scalar particle, like 10 to the minus 33 electron volts. Okay, so it's really, 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 really light. 10 to the 30 times lighter than the lightest neutrino or something, like really ridiculously light.
Which is already like one of the lightest things that we know.
Yeah, it's the lightest non-massless particle we know of,
Right.
right?
Massless would be zero. So
Yes, yeah, yeah, yeah. So the photon and gluon are exactly massless. Everything else is a mass, and they have way bigger masses than this would have to have. And furthermore, like when you have a really, really light bosonic particle like this, that means it can communicate a long-range force. And this, it might not be a very strong force, but it would be strong compared to gravity. So like it would screw up things like the dynamics of solar systems and stuff that we measure really, really, really well. So like it made me skeptical of these evolving dark energy models. But I brought this up in a journal club and said, well, what about these constraints? And somebody said, well, you have to use these other models with derivative couplings, which is just a special kind of coupling that gets around this objection. And I didn't know about that. So I'm reading about that now. Like there are these axionic dark energy models that do this. So they're kind of like these particles axions that we've talked about on the show before. I mean, they are axions, in fact, but they're not the kind that can make up dark matter. These are ultra, ultra, ultra light axions that could act as dark energy, and maybe they could go undetected, for example. So right now, that's my favorite, but it could change. I'm not an expert on this yet.
yeah. I mean, correct me if I'm wrong, but the impression that I've gotten is that, sometimes there's a theory that's like really it seems preferred by theorists, or it seems like everyone has a lot of faith in one theory because it all kind of makes sense and makes a lot of things fit
Hmm.
together. And so when experimental evidence comes up of that theory, it's like very easy to accept. But this seems like a case where it's evidence for something that is very hard to understand in terms of theory, where it's like maybe we need this other particle which would imply a new force that we've never detected before. It's like all stuff that's kind of hard to believe in a way, and that's making it a difficult result to interpret. Is that about right?
Yeah, and there's some famous quote. It's kind of snarky, and it was meant to be in jest. But there's some famous physicist, I can't remember which one, once said that you know uh, he'll never believe an experimental result until it's confirmed by theory.
Which is
And like that's of
snarky,
course
yeah.
backwards.
Yeah.
Yeah, yeah. But there is like a bit of truth to that. If you have some observation and you just don't have any good theory that makes sense of it, you're more skeptical, whereas if like you observe something new and you had a really good theory already that explained it, you might be more likely to jump on it, and believe it quicker. Now, in the end, it's data that wins. So if you have enough good data, it will overcome any of these prejudices. But at least early on, there are like theory biases that I think are pretty rational,
Hmm.
and that's just driving a lot
Hmm.
of this right now. I think a lot more people would believe in the Hubble tension, for example, being new physics, if there were like attractive theoretical explanations for it. But that's been so hard to write down stuff that works that people like are, maybe a little less likely to accept it on those grounds.
Yeah. So Rad's other question about this is a little more out there. So with respect to
Okay.
and some other people asked about this. I mean, this was a big result, so I'm glad we get to
Yeah.
talk about it. So with respect to the cosmological constant that's looking less and less constant, how do you think space-time will behave for an observer inside but near the event horizon of a supermassive black hole while the black hole is accreting? For the same observer, what would space-time look like while the black hole is dormant?
Well, I mean, I don't think, well, as far as I can think of anyway, I don't see any reason to think that the DESI result will change what we think things would be like up close to a black hole. Like, if you tell me that space is expanding differently, it doesn't matter. It doesn't impact how, my apple drop falls from my tree to the ground. Like, that's like, it's a completely separate problem. So, black holes are big and weird and everything, but the rate at which the universe is expanding doesn't really affect how they behave. So I assume black holes will behave the way that we've always thought black holes behave, which of course is weird and cool and interesting. But DESI hasn't made me reconsider that at all. Um, to my knowledge, no one else is thinking it should drive them to reconsider that, but maybe somebody out there is thinking something I'm not thinking of.
Okay, well, thanks, Rad.
Yeah.
Next question's from Julius. My question is, if astronomers can entertain the idea of an early period of very rapid expansion of the universe, how sure can we be that using the present rate of expansion is useful in determining the age of the universe? Great question.
Yeah. So oftentimes like textbooks or like quick summaries of cosmology will take like the current rate of expansion and relate it to the age of the universe. And that's usually assuming things like, the universe has been matter dominated or things like this throughout its whole life or something like that. In our real universe, you need more information than this. You need to know like when was matter the main thing, when was radiation or relativistic particles the main source of energy, when did dark energy take over, all this stuff. And another way of putting that is you don't need to just know the rate of expansion today. You need to know the rate of expansion like the whole across cosmic history. And if you know that, then you can get the age of the universe quite accurately. Now, I should say what we mean when we say the age of the universe. We mean how much time has passed since the universe was hot and dense and all that stuff. We don't know what happened in the first second after the Big Bang. And when we say first second, we're being again a little confusing. What we mean is if you extrapolate backward naively, you get to a point of t equals zero where the Big Bang was. And let's admit we don't know what happened in the first second, or at least fraction of a second. And when I say the universe is definitely 13.8 billion years old, what I mean is that there's been 13.8 billion years from that end of that era of ignorance, a second in or something, to the present day. So that era from a second afterwards is 13.8 billion years. And if you told me that you thought something really weird happened, maybe there was something before that, what we're called the first second, maybe inflation went on forever. That's one real possibility. So, like, clocks are all completely different than you think. Like, that's possible. Maybe there's some sort of cyclic universe, and like that hot, dense part of the Big Bang was just one of many times that the universe has been in that state in which case that's all fine. Then what I mean by the age of the universe is how long since it was in that hot and dense state most recently. Um, but like I said, you don't need just the current rate of expansion to do that. You need the rate of expansion over that cosmic history, and that's what we use when we calculate that number.
Yeah, and just to clarify, when you say matter dominated and this and that, the reason that you can go between talking about rates of expansion and, what matter or energy was in the universe is because the whole reason the universe is expanding is because of what's in it.
Yeah.
And if it had, now we're in this period that's dark energy dominated, you said. So that means that's why our universe is expanding at an accelerating rate. But at earlier times when it was matter dominated, it was expanding at a
Uh-huh.
slower rate. And so whatever's in the universe is determining whether it's expanding or contracting it and
That's
at what
right.
rate.
And the first thing you do in a graduate cosmology class, including the one I'm teaching right now, is you take Einstein's theory of general relativity, and from it you derive these things called the Friedmann equations. And the Friedmann equations tell you how fast the space should expand, depending on the geometry of that space and what kind of energy it contains. If you know those things, you can work out how space should expand. In our case, our universe doesn't have any appreciable geometry. It's what we call flat. And then we need to know things like how much matter there is, how much dark energy there is, how many relativistic particles or radiation there is. Once you know that, you can work out the whole expansion history.
Okay, cool. Well, good question. So our next one's from Paul G. I'm fascinated by the long, slow cooling theorized for white dwarfs,
Hmm.
tens of billions of years or longer before they're reduced to black dwarfs. Are there any mechanisms, however exotic, that might accelerate this cooling? Interactions with fields, increase angular momentum, etc.
Yeah, there are. So the way, so I mean, just think of a white dwarf. It's not. There's no fusion going on, so it's not like creating any new energy. There's not releasing any, new heat. It's just a hot thing radiating its heat into space. So it's like kind of like if I just took a big metal ball and heated it up. I didn't melt it, but I heated it up, and then I stopped putting energy in, and it just kind of warms the surrounding environment and slowly cools down. It's just like that. So in this case, if you wanted to make that metal ball radiate faster, you would have to give it new ways to radiate. And the same thing is true with a white dwarf. And what you might imagine is that there are other kinds of particles that exist we don't know about yet. They'd have to be pretty light particles, and they'd have to have very, very weak interactions in order to explain why we haven't seen them yet. But these things could be produced in the core of a white dwarf and kind of like just radiate out and carry away energy faster than a white dwarf would radiate just from light alone, and that could cause it to evolve more quickly. And in fact, by looking at the rate at which white dwarfs actually evolve, we can put constraints on these kinds of exotic particles that we might hypothesize.
All right, next question. Bill Quirk asks, great name, by the way, what happens next at CERN? With supersymmetry seemingly out of reach, what will experimental physicists be looking for?
So, I mean, you're right, Bill, that like supersymmetry was one of the things top of mind when the LAC turned on. And, there's still new constraints on supersymmetry coming out all the time. But yeah, it's not front and center the way it was. A lot of our favorite supersymmetric models are now completely dead because of the LAC. So that's a great scientific achievement to test a theory. And in most versions of supersymmetry we would have been excited about 15 years ago are no longer viable. But there are also lots of other things we want to look for, right? So I'm writing a paper right now, just to give you a random example, and there are new spin one bosons, what we call a Z prime in the theory I'm working on, and I needed to look up the latest results from the LHC to find out which parts of my theory were ruled out. And like the paper I was reading, I think was from less than a year ago. And it had new constraints that were tighter on these particles, and I had to take that into account. So, like the LHC is still teaching us new stuff kind of all the time. And it's not just, you know, new Z prime bosons or new supersymmetric particles or anything. Like the list of things they're looking for is vast. It's a huge, wide net looking for kind of every credible theory that somebody can write down. There'll be some grad student at the LAC whose job it is to write their thesis on that. It's literally thousands and thousands and thousands of different analyses looking for different things. Now, farther down the line, I mean, LAC is constantly changing and being upgraded and stuff. And there's going to be something called the high luminosity run of the LAC. So, part in particle physics, the luminosity just means like how many times a second are you colliding particles together. That's what they mean by luminosity. So in the we call it high luminosity LHC run, we're going to have way, way, way more collisions to study. And that will allow us to study theories that have like smaller event rates than you would normally expect, than you can currently test. So things that kinds of collisions that are more rare than we can currently test will become within the reach of this. And then, like even further down the road, I mean, we certainly hope that the Large Hadron Collider won't be the last thing we build at CERN. There are people who are advocating for a electron positron collider at really high energies in the same CERN facility. Eventually, that might get turned into a something like 100 TeV or 50 TeV proton-proton collider. So something like the LHC, but even bigger. Um, so, if all goes well, we'll be doing exciting world-class particle physics at CERN, well into the 21st century and beyond.
Yeah. I mean, it's more exciting for physicists sometimes when a theory doesn't get validated because it means that something weirder is happening, right?
Yeah, I mean, there have definitely been points in the history of science where everybody expected one thing, and when they measured the other thing, that really pointed them at something real, like something important. I mean, like think about when, Michelson and Morley measured that the speed of light was constant. Like it really wasn't supposed to be. Nobody thought it would be. Everybody thought it would be different depending what frame of reference you were in and all this stuff. And that like paved the way for special relativity and Einstein to walk in. So from the what we call the electric hierarchy problem, or equivalently the relatively light mass of the Higgs boson, particle physicists, or lots of us anyway, really thought that supersymmetry would have to exist and those particles would be within the reach of the LHC. um, we haven't seen those particles, so we were wrong. Um, but it leaves the question completely open. Like, so what is the solution to this problem? Like, what makes sense of this? And we don't know. And maybe with a little luck and perseverance, we'll figure out what these tea leaves are telling us. But right now, I think it's just a completely open question.
Cool. So our next question is from Simon Carter. We know the Big Bang and its subsequent expansion has created our observable universe, but assuming there is a universe beyond what light has had a chance to reach us, was this also caused by the same Big Bang? So I assume they're referring to, we talk about the CMB being the light that is the oldest light in the universe that's reaching us now, but maybe there was light that was farther away that's never going to reach us,
Sure.
right? And so the universe is probably bigger than what we can observe.
Right. And then you have to ask, like, there's a matter of definitions here, right? If there's a place in space somewhere, there's a piece of space somewhere that can't even in principle interact with our piece of space or vice versa. Like, is it in the same universe then? I don't know. Anyway, it's food for thought, but it's certainly the case that like we are surrounded by a horizon beyond which nothing can reach us and we can never reach, we can never influence, we can never see, we can never learn about, etc. Um, and there's no indication that like space just ends at that horizon. Like there's nothing special about that place. It just happens to be far enough away that light can't get to us from there because of how fast space is expanding. So I think I assume anyway that the space continues pretty much similar to our space beyond that, at least for a long, long way. We don't know how long. And all that came from the same Big Bang, right? So all the same hot, dense state expanded forth, bringing forth all that space. That being said, it's completely possible that if you travel through space far enough, like if you could go faster than light, say, and like visit all these places, you'd find places that don't look at all like our universe. Maybe there'll be places where the laws of physics are different and different kinds of particles exist. And then I think I would really insist on calling it a different universe, right? This is even though it might be spatially connected, although not causally connected to our piece of space. And you could also imagine spaces that aren't even spatially connected. Maybe whatever brought our universe into existence brought other patches of space into existence, and there are like no lines that connect those spaces to our universe. Maybe they're just like not connected. That's a perfectly logical possibility too. Um, I don't know how you'd ever test that. It's probably not. It's certainly not readily testable. Maybe it's not even testable in principle. Who knows? Um, but yeah. So I think kind of everything Simon suggests is on the table. There's probably a bunch of space that emerged from our Big Bang beyond our observable universe. There could very well be space from our own Big Bang that is unrecognizable to us. May or may not be, I should say. There could have been multiple Big Bangs. There could be multiple pieces of disconnected space. Kind of anything is possible. I'm pretty open-minded when it comes to this stuff.
Yeah. It made me think if I wonder if there's another way to think about it where like the observable universe kind of forms a big sphere around us, right?
Hmm.
Like we're at the center of it because the observable universe is defined by the light that has been able to reach us. But if you say we're to hop to a planet that was on the edge of our observable universe, they would have an entirely different
Yeah.
sphere that is their observable universe that extends beyond ours.
Right. And I assume those people aren't, or whoever they aren't observing like some edge of the universe beyond our horizon, right? I mean, they could be, I guess, but there's no reason to think they are.
Right. And the odds are low that like we're the only point that we perspective that we know of. So the idea that it's a unique one is probably low odds,
I would think so. That's
right?
certainly how I approach it.
Yeah.
Unless you think we're in some computer simulation and the person designing the simulation's only interested in making a universe that we can see.
Yeah. I mean, they already wasted time on all the other galaxies. So
Yeah.
I don't know. Okay, cool. So maybe this is actually a perfect lead into the next question from Ian, which is, could you name one conundrum that you think we may never know the answer to? So you got at least one. So they say, as a lay person who knows what I know through your great podcast, thanks, it seems we might be inching towards understanding certain problems, like dark matter, but will we ever understand the singularity at the beginning of time, for example?
Yeah. Never is a really long time. And like I don't think I'm prepared to say we'll never understand anything. Anything that like makes logically coherent sense, like something that could be understood. Um, so I
It also
think
depends what you even mean by understand,
that's
right?
true. That's
Like,
true.
do we need to be able to predict everything that happens to understand it, or to manipulate a universe to, or create a simulation of a universe to understand ours or something, right?
There were a lot of times in the history of science that a question seemed completely unanswerable, right? And in many of those cases, we've now answered those questions.
Hmm.
So, like, I don't want to say that just because I and my, ape brain can't right now, imagine how we're going to solve certain problems, that, I don't know, in the 27th century or something, with the super AI that now controls the observable universe and blah blah blah, like that they won't be able to figure it out. Like, I'm not prepared to make any such
Right.
statements.
Yeah. Also, I'm sure there's like the other world of what we don't know that we don't know, right? The questions we haven't thought to ask yet.
Oh yeah.
Like someone from the 12th century would not be able to ask the question of what happens near a black hole,
Right, right.
it wouldn't cross their mind. So,
Or even if you ask them a question, like, I mean, just 110 years ago, if you asked a physicist, like, how
Mhm.
could space have come into existence or change? Like, nothing. You would have crickets. Like, the Newtonian physics does not allow for that. It's not a thing. But Einstein gave us a whole long list of new questions to ask, about cosmology and black holes and all sorts of things. And I'm sure that's not the last time that will happen.
It's fun to think about, though.
Agreed.
Okay, the next question's from Jem. I've seen various popular science news come up recently. This is again about dark energy, So the Popular Science News has recently been proclaiming that dark energy in the standard model of cosmic inflation is being superseded. This is attributed in part with the greater data resolution and measurements of type 1a supernovae, as well as the new work developing the timescape model of cosmic expansion. I don't know if you've heard of that, Dan. I actually recently just saw the PBS space-time video about that.
What is timescape?
My understanding is that it's an idea that dark energy could go away if you consider the different rates of time passing in different voids of space depending on their matter density and energy density. Like maybe there are voids of space that like expand faster because there's no matter in them, and other parts of space that are more crowded expand slower. That's my vague under what I think it is. I'm not sure.
Okay.
So, they ask, I'd love to get your insights into whether any of these other models, particularly the timescape model, holds any water, or if this is just overblown science journalism. In your opinion, has there been any major updates recently that could reasonably overturn dark energy theory or even address the Hubble tension?
So let me clarify one or two things. I think at one point in that question, it was said that these new observational results had some bearing on inflation. I don't think they do. I don't think anything that we do or don't know about inflation is impacted by this.
Yeah, so let's clarify, because I understand
Yeah,
that the words get confusing because they all sound the same and
yeah,
are
yeah.
about very similar things. So there's like the expansion of our universe that's caused by dark energy, which is what's happening now, and the term inflation just uh corresponds to the time in that very very earliest second or so tiny or fraction of a second after the Big Bang when there was like hyper expansion, right? So we're the current expansion of the universe we don't refer to as inflation. So it's kind of a different model, right?
Yeah, yeah, yeah. Yeah, so yeah, just like you said, inflation was something primordial, something happened very early. And yes, it kind of looks like dark energy, but turned way, 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 way down in intensity. But yeah, they have something in common, but they're different things. They're different things. Um, so it is certainly the case that cosmologists are interested in the DESI results that suggest that maybe dark energy is evolving. Uh, I don't know anybody who has called it a discovery or anything so definitive yet. It's more provisional. It's like there's some evidence that dark energy might be evolving, and we all agree we need to take a good look at this and see if it's true. But that's kind of where we're at. We're not ready to overturn everything or anything yet. Um, and then like I hadn't heard of this timescape stuff until like literally right now. And kind of while I've been talking, I've been Googling. Um, and it sounds like it's this David Wilshire's idea that, we have some sort of inhomogeneity in the distribution of the universe, and that leads to this illusion of accelerating expansion without real dark energy. Now, I don't know exactly what Wilshire's saying in detail here, but these ideas have gone back to a lot of people, like, for forever, for so long as we've had dark energy. I remember when I was a postdoc at Fermilab, you know, 20 or so years ago, almost 20 years ago, and people like Rocky Kalb were really advocating for things like this, or at least arguing it was plausible. But as the data got better, it just got less and less plausible to me, or not to everyone, to the community. You had to like put yourself in a very specific part of the universe that had significantly different density than other places did on average, and you had to be kind of almost exactly in the middle of it, like in a like a spherical kind of oddball configuration, and it just as the data got better, this looked harder and harder and harder. Also, we've measured the presence of dark energy in a lot of different ways now, and they all kind of just look like the universe's expansion rate is accelerating. It doesn't look like these. inhomogeneous models that were occasionally put forth. Um, so unless there's something like fairly different about this, timescape picture, I don't think this is something that's particularly likely. I'll point out, just I'm doing cosmology every day. I talk to cosmologists all the time, and I literally only heard of this, 30 seconds ago or something. So
Yeah.
like this is not something that cosmologists are actively thinking about, at least not very
Hmm.
many of them.
Yeah. That's a hard thing in science communication sometimes because I mean, I think especially recently there's been some corners of media or big mainstream corners of media that make some sort of case that like if something is an idea, say, about cosmology and cosmologists aren't talking about it, it's because of some conspiracy or like, and usually that's not the case. There's like a
Yeah.
very natural evolution of like someone puts forward an idea. Maybe that idea is interesting, but if you take it out of context and make it seem like the best idea, you're kind of ignoring the fact of the natural progression of the ideas out there. If it's a good idea, other cosmologists will naturally go towards it and look into it more and like ask more questions about it. And so the ideas to really pay attention to, I think, as science journalists and communicators are the ones that are already getting a lot of attention in the scientific community because those have been really vetted.
Yeah.
And like other ideas might have really interesting pieces, but they're still kind of like fictions unless they're like, or like to prop them up to the same level of something that's been really thought through and interrogated can be problematic sometimes, which is tough because we also, want to share new ideas and want people to be excited about science. So
Hmm.
it's a tricky tension.
So I'll comment on that in a minute, but I want to say for everybody who wants to know more about this, there's a nice Ethan Siegel article on this. Just it's called "Ask Ethan: Can a Lumpy Universe Explain Dark Energy?" He takes his head on. So and it looks like he's going to cast some shade on this interpretation. He usually is pretty good at that sort of thing. But you're totally right, Shalma. Like there are more scientific hypotheses put out there than could ever be followed up on in any depth, right? Every day there are hundreds and hundreds of new physics papers on the preprint archive. Maybe I read on a good day 3 of them, so like I just can't know about everything that's going on. And I have to look at these things and quickly make some sort of assessment. Is this like idea important enough for me to really invest my time in? And, like other scientists, I think we are, we weigh a bunch of considerations like, do I have tools that will help address this question? Does this, hypothesis or theory, does it solve problems in a compelling way? Does it seem well motivated for other reasons? Like, is there any evidence for it? Things like this. And we can end up ignoring a bunch of stuff, or not ignoring, but like not investing much time in a lot of ideas because of just the reality of there not being enough hours in the day to think about everything at infinitum. And that's not a conspiracy. That's not anybody trying to control anything unduly or whatever. It's just a matter of like, where is our our hours of sweat and energy going to go into? This does not sound like a theory I want to put much time into. It just doesn't seem very likely to be true. Um, and by the way, if it were true, and there were good arguments for it, somebody could make a name for themselves by promoting it successfully. So like there's some self-correction to this in the model. If something's being ignored, it actually provides an opportunity for somebody to like kind of get good attention by promoting a good idea that isn't currently appreciated. Um, so when an idea for a long time goes unappreciated, there's usually good reason for it. And I don't know of examples in the history of science where people disregarded a theory for a long time for any number of reasons, and then later it turned out to be true. Like that's just not what seems to be playing out in the history of
Mm,
science. Usually people
yeah.
have pretty good judgment about these sorts of things.
Right. And I'll point out, like, when you were describing as a working cosmologist looking at the recent papers that come out and picking out 3 to read each day, if you're a popularizer of science, or someone who's trying to reach a lot of people or get a lot of engagement on social media, you're approaching the papers with a very different
Yeah.
question. You're not asking what's worth my time in terms of a real scientific investment. You're asking, like, what would get the most engagement and, like, be exciting and be most different maybe to people. And sometimes those things are kind of, you end up with different answers.
Hmm. And I
Yeah.
think these things have to be balanced, right? So, yeah, I mean, I find it frustrating when papers that 99% of experts would read and say, this is just flatly wrong, get picked up by science journalists without saying that and say,
Mm.
maybe this weird thing's happening. And like, well, no, here are 6
Yeah.
really good reasons why it's not. This is just a bad paper. It's false. It's wrong,
Yeah.
whatever. And this happens all the time.
Yeah.
It usually doesn't happen at the most, I don't know, trustworthy of science, yeah, of science communications media, but especially with the proliferation of
Mm.
kind of small websites and kind of one-off rapid generation
Yeah.
science articles.
Hmm.
There's more and more of
Yeah.
this, and
Yeah.
these
In
things do
general,
well on social media.
right, right. If someone's putting out, like, a news article a day after the paper got released or something, there's a chance it's not that well researched.
Yeah, that's true too.
That's also true. All right, but enough of that sidebar. We have a few more questions. So this one, I actually don't know what it's about, but maybe you will. Another question from Rad.
Okay.
Did the S8 tension go away with the latest kids result? To me, this
Oh,
is
yeah,
a
yeah.
different language, but
So
maybe you know what.
S8 is also is this means the same thing as sigma 8. And sigma 8 is a cosmological parameter that tells you how much clumping there is in our universe at a certain length scale, 8 megaparsecs. So like it's just a way of normalizing how much clumping there is of the matter in our universe. And it's one of the many cosmological parameters you measure. And some of the measurements of this were kind of in discordance with other measurements. And people were wondering why. And it was called the sigma 8 tension or the S8 tension. Um, now, I might irritate some of my colleagues by saying this, but I've never understood why this was considered a big deal. It was never very statistically significant. It was like 2 or 3 sigma. And I don't know, like it didn't, to me, it didn't pass the threshold of statistical significance to merit the kind of attention it's received. So I don't know. I think it was probably never that big of attention to begin with. And some new data have, including the kids stuff that I forget what kids stands for, KIDS. But well, let me find out what that is. Kids cosmology. Yeah, the kilo degree survey, kids. This and other data have, in some cases, seemed to take some of the steam out of this tension. I don't think everyone would agree that there's no tension or something like that. I don't think that's the case. But there was never that much tension, and maybe it's a little bit less now.
Hmm. Okay. Okay. 2 more questions. The next one's from Dr. Mark Anderin. If the total energy of a particle or object is a combination of its stored energy or intrinsic energy and its kinetic energy or the energy of its motion, and motion has to be relative to something else, there's no absolute reference point in space-time, does that mean that the total energy of a moving object is variable and depends on your reference frame?
Yeah. I wouldn't
Yeah.
say variable necessarily, but definitely depends on your reference frame. Yeah, absolutely.
Yeah.
Yeah, that's that.
That's that.
Yeah. I mean, okay, I guess I'll say more. Like, yeah, if I have an electron just sitting there at rest, and then, in my frame of reference, it's not doing anything, then that thing has an energy equal to the mass of the electron. If, on the other hand, I'm flying by it at nearly speed of light, to me, it looks like that electron's moving towards me at nearly speed of light, and that has way more energy. So, yeah, energy is a reference frame dependent quantity, as many, many quantities are.
Yeah.
There you go.
And that's that, yeah. Cool. And then our last question. Okay, this is from James. So James asks, is there any way in which it makes sense to take solace in the block universe? I specifically have in mind this quote from Einstein when he is comforting a colleague's wife after a death. People like us, this is the quote from Einstein apparently. People like us who believe in physics know that the distinction made between past, present, and future is nothing more than a persistent, stubborn illusion. So in the death of a loved one, does it actually make sense to take solace in something like general relativity?
This is an awesome question. So let me start by explaining why I think Einstein thinks of the past, present, and future as a stubborn and persistent illusion. Um, so, and by the way, like philosophers still debate some of these things today. Like this is an active question in certain fields of philosophy. For example, there are um, people who might argue that the only thing that exists right now is the present. Like, and there was a past that once existed but doesn't exist now, and in the future there might be a new thing that exists, but that doesn't exist now. There are other people who think the past exists and the present exists, but the future doesn't yet, and maybe that means like the future is contingent, things like this. But relativity gives us some insight into this question, namely the order in which events happen can be different depending on which frame of reference you're in. So if you think event A happened before event B because you're in that frame of reference, and somebody else equally correctly thinks event B happens before event A because of the frame of reference they're in, then we really can't say that, you know, the time that event A happened is on a different plane of existence than the time at which event B happens. Like they kind of all have to exist together in the same way. So, taking this a little bit further, it seems like all of the events that have or will ever happen are just kind of laid out there as part of reality. And yeah, we observe into slices of that reality at a time, at one moment, but it's all like out there and real. And I think that's what Einstein means when he says it's, time, the distinction between the past, present, and future is a illusion. Now there's the much different and much more human question about how you should feel about this. um I don't know if the death of a loved one would sting any less, uh knowing this or thinking this about the universe.
But if it does, then that's great. I
Yeah, yeah.
mean, grief is weird and not computable. I don't know. It's a if that helps, then I think that's pretty awesome.
I completely agree with that. And I would say I get some comfort from not seeing any reason to believe in free will.
This is a whole other
Yeah, but if
can of
time if
worms.
time is an illusion, then it's already happened, right? And if what's going to happen is just going to happen, then I'm kind of liberated from worrying about it all that much, right? Um,
Yeah, I mean, yeah, I don't think even the existence of free will, like whether or not we have free will to have intentioned actions, doesn't mean that we have the ability to control any outcome of any action, right? So I think it's
all true.
yeah, I don't know. I think maybe there's a comfort in just how feeble you can be and to not try to control everything because it's not possible. But I don't know. I mean, there's a lot here to say, so
We do have that I like the episode we did on free will, so people should go check that out if they haven't seen it already.
Episode 23, does physics allow for free will? But yeah. But yeah, so that was a great question. Thank you all for your questions. This was a lot of fun.
Yeah, that was great.